Beans. So I like beans, and in particular, I like to look at beans. But sometimes the beans look ugly, so I like to order them in a certain way. So I'm going to dump my problems on you, and I ask you this. Given a grid of 10 by 10 slots, with some beans already in the grid, and numbered beans 1 through 10, 10 times for each row, make it so that each row and column have the numbers 1 through 10 in them only once. But I need you to make a program that does that because you have too big of a brain. The problem then becomes, how efficient is it to solve this? Because I don't have too much time. I have to grow my beans. So there are two classifications of problems for our purposes, P and NP. The group of problems P are relatively easy to solve, and P stands for polynomial time. Then there's another group of problems called NP. You'd be forgiven for thinking it means non-polynomial time, but King Bean forgives all. And you would be told that NP actually stands for non-deterministic polynomial time, which is hard to solve but easy to check. Non-deterministic meaning essentially if we had a substantial amount of computers, we could check all the answers at the same time, and we could check all the answers at the same time. You could find a solution in polynomial time. Well, what does easy mean here? Easy means that the problem can be solved in a reasonable amount of time, and it could be the same amount of reasonable that my friends drink every weekend, because polynomials can have very large constants or exponents contained within them, but they are quicker to solve than problems that require exponential time. Well, what does solve mean here? Well, for our beans, it means that the more beans I have, the longer it's going to take to make the beans look how we want them to look in our grid. So in getting a solution to the bean grid problem described earlier, it would be in the classification of NP. But if I gave you a solution and asked you if it was correct, it would be P. Well, meaning NP it's an NP because you have a solution to the problem and it can be verified. There are some additional classifications that have been defined though, one of which was just called NPcomplete, which are all of the problems that if we can find a way to reduce one to polynomial time, however that is done, we can reduce all NP problems to the classification of P. Essentially, NP complete problems are all traveling salesman problems. They can be reduced to this, which asks, given a list of beans and the distances between each pair of beans, what is the shortest possible route that visits each bean exactly once and returns to the original bean? So it's a cycle. One other important classification is NP hard, which is simply just a set of all the problems that are at least as hard as any NP problem. Finally, my favorite, which is EXP, which contains a set of problems that require no less than exponential time to solve. For example, finding the perfect strategy in a game of chess on an n times n chessboard. It is important to note the model of the computer that is being used to analyze these problems. Typically, we assume that the computer is deterministic, which means that given the states the current beans are in and any additional beans given, there's only one possible action in which the computer might take. And sequential, which means one bean is operated on after another. The guys with big brains and that do things with computers and probably have a lot of beans because they get paid so much ask this very important question: does P equal NP? That is to say, are all the problems that become verified in polynomial time can also be solved in polynomial time? While this would be good for the computer people and my beans, it is widely believed that these two groups of problems are not equal. If we were able to answer this question definitely, we would have major breakthroughs in topics such as cryptography, algorithm research, game theory,